Okay, so thanks for coming out. Know who's keen here and who are the wimps? Question already.
The question, we do look like a different band.
Yeah.
Is it crazy to get like a quad band radio that has a 6 meter in it, and then just like a 2 meter and a 70 centimeter?
Is it crazy?
Yeah, it's just that when you read in the book,
Right.
it says that 6 meters is too far.
It seems to be.
Yeah, and I'm just thinking that's a lot expensive than buying like an HF radio.
Oh, I see.
That's one sort of the other.
Yeah. I guess it depends on what you want to do. A lot of people just operate VHF, which is 2 meters, 70 centimeters, using repeaters if you just want to talk to people locally. If you want to have more long distance contacts, then HF is where you want to be, probably 20 meters, 15 meters, 10 meters in the right conditions. Dave, who is our vice president, he's one of the instructors here, he operates on 6 meters a lot, he gets some reasonable contacts, across North America under the right conditions, and I guess that's what we're going to talk about today, population. Whatever you want to do, really.
I'm just wondering if it's like a possible thing to do with it. Sort of crazy because you get into 6, you just got, want to get into the others, and then you put the radio.
Yeah. A lot of the HF radios will go all the way down to 6 meters. It's not a band I operate on, so I'm not sure I can really. Dave is a 6 meter band, so he's the best person to talk to about that.
Okay, thanks.
Yeah. Okay, so we're going to look at propagation today, and those are the topics. I guess what I'm going to start with is a little review of things like radio waves. I talked about that previously. Just get an understanding of the terminology again, with things like polarization, understanding that, the nature of waves, and then we're going to talk about some of the effects. And there's a lot of interesting effects. I think this is where the magic happens, where we can use our understanding of the effects to allow us to communicate long distances. So that's really what today's about, understanding how that works. So it includes things like understanding the ionosphere, the way that works, understanding how the radio waves propagate from the transmitter to the receiver, this idea of skips, hops, bouncing off the ionosphere and off the ground. We also have to talk about absorption and fading, because the signal can get attenuated as it goes through some of these layers, and we need to understand where that happens, why that happens. What else have we got? Talking about the effect of the sun on propagation, because that is a big factor on our ability to communicate long distances. So understanding how the sun impacts on the ionosphere and what that means for us in getting our signals across. We're also going to talk about some of the technicality of understanding where the limits of operation are in terms of frequency. We'll talk about some of the effects at high frequency, VHF, UHF, and what people can achieve at those frequencies. Scatter is another factor. We can bounce our signals off. I'm not sure I call them objects, but potentially things in the sky. Could be objects, and beacons, and at the end I've got some sample questions. Now I noticed Steve put up a slide like this, which is the list of topics. This is a little bit different to what I put out on Wednesday in the slides, because I realized I didn't have all the questions, So this has 8 questions or 8 subsections. You probably noticed already, and if you've read RIC 3, you'll see all the topics that we have to learn for the exam, and they're organized by section or subsection. So propagation is one entire section, and there are 8 subsections. And these are the topics, which are largely what I just talked about. And there are questions in the question bank. Typically, each subsection has 11 questions, and you will have one of those 11 questions on the exam. So I'll talk more about exam preparation next Wednesday, but the exam will have 100 questions, and there will be one question on each subsection. So you're guaranteed one question on line of sight, ground wave, atmospheric waves, and one question on the next topic, or subsection. So basically, it's 1 out of 11 of those questions in the question bank are going to appear on the paper. So I talked about basically all these topics. That's what you're going to need to know when we get to the exam. And that's what we're going to talk about today. These slides largely come from the publisher Coax, and so I'm just going to. I put in some slides of my own, but this is one of theirs, and it's basically saying that your ability to communicate is dependent not just on one factor, but there are a combination of factors. And so in this picture representation, there's the operator. That is, you need to be skilled, which is what the last lesson was about, knowing how to communicate, what the right words are to use, even to the extent of if you're operating Morse code, getting tuned to hearing that sound, or if you're operating SSB, being able to pick out those the voices through the noise, developing that ear. So operator skill is one. Obviously the radio equipment is a major factor, getting reasonable quality equipment and having it do what we want it to do, filter out signals, tune, all of that. Antenna systems, we talked about those. And the final one is one in the bottom right, which is propagation, which is getting the signal from our transmitter to the receiver. And if we're operating at HF, that would be bouncing it off the ionosphere and off the ground, or off the sea, off the earth, in multiple hops. So that's what we're learning about. Okay, so this is the refresher. We've got radio are electromagnetic waves, just like light, just like all of these others, like gamma rays and X-rays. When I was studying, I actually studied physics and electronic engineering at university, and one of the days I was sitting in my engineering class, and we were probably talking about electromagnetic theory or something really obscure like that, and a light bulb went off because I realized that a lot of what we were learning in electronic engineering was the same thing I'd learned in optics in physics the week before. And it makes sense because electromagnetic waves, radio waves, are light. And if you think of radio waves as light, and you understand the properties of light, then it helps to understand what's happening with radio waves. So we've got a whole wide spectrum of electromagnetic waves, of which some in the middle are light, going from high frequency to low frequency. So the low frequency ones are the radio waves. We go through infrared, light, then ultraviolet, X-ray, and gamma rays. You need to pay attention a little bit to ultraviolet and X-rays, because those are the things that we'll talk about later, coming from the sun, which are impacting the way we can communicate long distances. Okay, so we must have done that. So propagation is really the idea that we are getting a signal which is really an electrical signal, voltage, oscillating, being emitted from an antenna at a transmitter, and then propagating through space to a receiving antenna, where it's picked up and converted back into whatever the messages that we're trying to get across, whether it's voice or Morse code or data. Okay, so I wanted to give a little bit of historical context on how this happened, and I thought this was interesting. We first discovered propagation, and this was back in the late 1800s, using a piece of equipment like this, which is basically a coil with a spark gap. So this is a spark transmitter, there's a coil there, there's a spark gap, and there's a circuit over here. And basically we're at high voltage source, charging a capacitor. When the capacitor gets up to a high voltage, you get a spark across, which will then really provide an impulse to this tuned circuit, so we've got an LC, and that circuit then oscillates. The spark ends, and we get this decaying signal here. Rather than having what we now call continuous wave, we get this damped oscillation. And that's how radio was first developed, and we would use this to communicate. So originally, people thought that this ability to induce a signal in a remote piece of equipment, and the receiver was very similar to this. It was basically a tuned circuit with a spark gap. And people found, who was this? I can't even remember who did this. Was it Tesla? I don't know. One of those people. What they found was when they operated this transmitter, they could detect a spark in the receiver. And they thought originally this was just magnetic coupling. But later Maxwell came along and developed a theory for electromagnetism, and this equipment was able to demonstrate that theory because we could propagate the signal over longer distances. So it wasn't just magnetic coupling, but it was electromagnetic propagation over longer distances. And these things were, this idea of the wave traveling, originally was called a Hertzian wave, and people would send Morse code using these damped impulses. So this is where the idea of the original damped wave comes from, and then we developed the idea of having a continuous oscillation, and that's what we call continuous wave, and that's why when we send Morse code now, we describe it as CW, continuous wave, because we don't use spark gap transmitters anymore. Well, that's just a bit of historical context. It's not going to be on the exam. So we get propagation traveling from transmitter to receiver, and it travels like light. So if we understand what light does, then we understand what radio waves do. So light travels in straight lines, we know that. And it travels through a vacuum. It doesn't require a medium like sound. So when I'm talking here, my pressure waves are traveling through the air, and if we took out the air, you wouldn't be able to hear me because it requires a medium. Electromagnetic waves don't require a medium. They travel through space, the vacuum of space. The way they travel follows this thing we call an inverse square relationship. I don't have the box with the balloons in. So the way I would normally demonstrate this is the wavefront emanates from the transmitter going out in all directions. At least if you remember the isotropic radiator, the ideal radiator that goes out in all directions. So if you imagine the wavefront traveling out in all directions, the amount of power that is